Yeah, so I just want to say first thanks to everybody for joining us today. I want to say a few words about next week's speaker. So next week, Dr. Thomas from Yale University will talk about ocean carbon cycle. So if you can join us. But today it's really my pleasure to introduce Dr. Sim. So Dr. Sim is a geodynamicist. She used numerical methods to understand Earth processes. And she did her PhD at Scripps in San Diego. During her PhD, she built a new numerical model to understand magma transport beneath mid-ocean ridge. And I think that's what she's going to talk about today. She defended her PhD in 2018, right? Yeah. And joined the Carnegie Institution as a postdoc fellow, during which she looked at this time the cycle of carbon transport in subduction zone this time. And so she's now a research scientist at Georgia Tech for a little bit more than a month, if I understand. And so a few words about how I know Joyce. So I first met Joyce at AGU, I would say, a few years ago now. And I actually thought she was a postdoc as me at this time flies. And now actually it turns out that she was a brilliant PhD student. So I just want to say that I always enjoy talking with you at conferences. And I'm a bit sad that we are not going to be able to do that this year, but I'm also very happy that you accepted our invitation for this seminar. So thank you and welcome. And that's you.
Cool. Thank you so much, Sarah. Thank you. Well, first of all, hello, everyone. Thank you for having me here and coming to my talk. Yeah, it's really a pleasure. So, like Sarah alluded to, I'll be talking about melt transport beneath mid-ocean ridges today. She also mentioned that I do work on subduction zone carbon transport. But I won't be talking about that, but if you are interested, we can always talk more about it. Let's see. There you go. So although I'll be focusing on mid-ocean ridges today, I do work in general on trying to understand melt transport at tectonic boundaries or kind of fluid transport in general at tectonic boundaries. So why tectonic boundaries? So shown here are the tectonic plates that are moving on top of the asthenosphere. These plates kind of interact at these boundaries, and where they kind of collide and pull apart and kind of slide past each other, sometimes generating hazards like earthquake. Tectonic boundaries are really a crucial connection between the Earth's interior and the surface where exchanges of energy and volatiles occurs. And it's really where all the action is at, and that's why I'm really interested in studying them. So even though it's so interesting, there are so many questions as to how they work. And one of the big questions that I'm interested in is posed here: how did the continents form and co-evolve with plate boundaries? And of course, this is kind of a question that's tied into the early Earth. So to try to get there, to try to start to understand this, how to answer this question, we kind of have to try to understand what modern day Earth looks like. So I start off with mid-ocean ridges because they are just much simpler system compared to subduction zones, and yet there's still so many questions such as melt transport and what separation plate separation might look like in the past, etc. So mid-ocean ridges are where oceanic plates are moving away from each other. So here's a bathymetric map showing mid-ocean ridges as bathymetric high, as highlighted in yellow. I think you guys can see my cursor, right? I hope so. So what do you see when you go to these ridges, right? If you can guess, you see black nothingness, because the average depths of these mid-ocean ridges are 2,500 kilometers. These are, well, okay, sorry, 2.5 kilometers, I should say. That's like 25,000 100 kilometers, that's very, very deep. So these are very harsh environments that are very difficult to observe. So mid-ocean ridges produce most of the world's volcanism. And yet we don't really understand how melt actually forms and migrate underneath. It is really a way for the mantle to communicate with the surface, and that's why it's pretty important to understand that. So the classical view of creating this volcanism and melt is by decompression melting. As two plates are pulling apart from each other, it causes the mantle to upwell, and therefore decompression melting. The melt generated by this process forms new oceanic crust at mid-ocean ridges. As this oceanic crust moves away from the ridge axis, it cools and deepens according to half-space cooling. So since each piece of a lithospheric plate is rigid and it moves at different rate relative to one another, mid-ocean ridges vary in how fast they're spreading apart. So it's pretty common to categorize mid-ocean ridges by their spreading rates as shown here. So ultra slow on the left here, and then very fast on the other side. So the fastest spreading rates are observed in the East Pacific Rise, and the slowest is at the Geophysical Ridge up in the Arctic Ocean. So you might expect some systematic differences from the range of spreading rates observed. One of the fundamental observations at mid-ocean ridges is the amount of oceanic crust produced. So here's a plot of crustal thickness in kilometers on the y-axis and half-spreading rates in centimeters per year on the x-axis. And pretty much is showing a seismic the crustal thickness based on a seismic observation. So what I want to point out here is that oceanic crustal thickness is fairly constant for half-spreading rates of more than 1 centimeters per year. And most of oceanic ridges are spreading at more than a half-spreading of 1 centimeters per year. So we expect most of the data to be in this part here, like 6 to 7 kilometers. So this 7 kilometers is made out of different layers as shown on the right. So you have the pillow lava at the top, and then followed by sheeted dike complex, your gabbro, and then a layer gabbro. Then you have the upper mantle. So this is where the moho should be. So the oceanic crust is formed within a few kilometers of the ridge axis, regardless of spreading rates. So a slow spreading rate ridge axis looks pretty different from a fast spreading rate ridge axis. And you can kind of see this when you go on Google Maps or Google Earth, and you can kind of see that at a slow spreading ridge such as the Geophysical, lava is kind of erupting into an axial low valley, and at a fast spreading ridge, lava erupts at an axial high, shown on the right here. So the spreading rate kind of determines the structure of mid-ocean ridges, but then you have a narrow volcanic zone at the surface, at the ocean bottom, regardless of the spreading rate. So this might lead you to have the expectation that melt is generated in the narrow zone. Well, in fact, wide regions of melt has been observed beneath mid-ocean ridges by various geophysical methods. So at the East Pacific Rise, where the spreading rates are pretty fast, on the left here, I'm showing seismic tomography kind of shows slower phase velocity beneath the ridge axis, and it kind of increases away from it. This has been interpreted as presence of melt in a wide region of a few hundred kilometers beneath the mid-ocean ridge. And similarly, at another part of the East Pacific Rise, you have magnetotelluric inversion from a electromagnetic survey. And they observe a conductor beneath the ridge axis that also is kind of indicated by this red blob here on this right-hand figure. That also suggests the presence of melt in a fairly wide region at depths. So we see evidence that melt is generated in a fairly wide region and that it forms oceanic crust in a fairly narrow region. So how does the melt focus? There must be physical mechanism present that focuses melt from this wide region to this narrow region as it erupts on the oceanic surface. So several mechanisms have been proposed, two of which I am highlighting here. On the left, rich suction is due to oceanic plates kind of pulling apart, and because of its incompressible material, and also by conservation of mass, it creates this suction that pulls melt right at the ridge axis. And on the right here, we have what we like to call decompaction layers, where buoyant melt is kind of just rising and it encounters a cold, strong lithosphere. And because the oceanic lithosphere kind of cool and deepens away from the ridge axis, it creates a naturally sloping interface where melt piles up and gets diverted and moves towards the ridge axis. So just to give you a rough idea of where I'm heading towards, like by the end of the talk, I will conclude that on top of the two melt focusing mechanisms that I just highlighted, we also recognize in our model another melt focusing mechanism, which we'll call melting pressure focusing. So in this illustration here, these are the previous models on the left that kind of illustrates this decompaction layers and also this rich suction. And on right is kind of highlighting that third melting pressure focusing. So I am a modeler. I solve equations to try to understand the Earth. So in traditional geodynamics, we tend to solve single phase flow. So we solve for conservation of mass, momentum, and energy for a single phase, which is usually the solid matrix that deforms as like it's a fluid over a long time scale. But I do use two-phase flow. It just means that I'm dealing with two materials that have very different viscosity. So in this case, I have a solid mantle matrix. Well, it's treated more like a solid, but it also flows over a very long time scale. And the fluid is this melt, which is melted from the mantle. So similarly, similar to single phase flow, for two-phase flow, essentially we'll have to conserve mass, momentum, and energy for both the phases. So here are the equations that I solve. I really just need you to focus on one, which is the Darcy equation. So this is essentially kind of like the conservation of momentum for the fluid phase. So on the left-hand side of the equation here, we have phi, which represents porosity or melt fraction. And then you have VF, which is fluid velocity, and VS is solid velocity. So essentially on the right here, you kind of have the fluid segregating from the solid matrix. And that is balanced with the right-hand side. The big K is permeability of the solid matrix. And then you have mu, which is your fluid viscosity. And then you have your pressure gradients. So experimentalists have melted mantle-like aggregates in a lab and have image melt as shown here with increasing porosity. They show that melt forms interconnected pore space even at very low porosities. So here, the void is the part that's solid, and then the gray and red is the part that is melt. So from A, I think this is a 0.02% melt, and then you have D, which is about 0.2. So that's like 20% melt. And so the point here is really to drive home that even at very low melt fraction, the melt pore space are very interconnected. So we expect them to have high permeability and therefore implies efficient melt transport. So overall, the full governing equations are fairly hard to understand. This is why to try to understand what the different pressure gradients that's focusing melt from a wide region to a smaller region, we decompose the pressure into various forms to help us better understand the different processes. So here you have the total fluid pressure that's decomposed into compaction, lithostatic, and dynamic pressures. So dynamic pressure is essentially what, when you have the solid part being pulled apart, that's kind of creating a pressure right at the ridge axis. And lithostatic pressure is whatever you have that's piled on top of the point you're looking at. And compaction pressure is the unique term here and is defined at the bottom. So it's defined by the divergence of a solid velocity scaled by the bulk viscosity. So the divergence of solid velocity, you can think of it as the expansion and contraction of the solid mental matrix. So you can think of it like a sponge, and the bulk viscosity is kind of how hard it's resisting this expansion and contraction. So the sponge would be, the bulk viscosity would be how hard it's resisting the squeezing and releasing. So now we put this pressure decomposition back into our favorite Darcy's equation, and we have this equation below. So really what this is telling us is that melt segregation is due to the various pressure gradients. And because melt is naturally buoyant when it forms, any horizontal pressure gradient that is going to focus melt towards the center has to fight with, has to be the same order of magnitude as buoyancy. So now I'm going to try to explain the different focusing mechanisms that I kind of presented before in terms of the pressures that I just talked about. So for ridge suction effect, it is essentially due to the oceanic plates pulling apart, and because of conservation of mass and an incompressible material, when it's pulling apart, it creates a dynamic pressure right at the ridge axis, and that kind of pulls melt towards it. And this is what Spiegelman and Mackenzie were alluding to in their work in 1987. And in decompaction layer, as bone to melt is rising in a weaker mantle that is permeable as well. It encounters a cold and therefore strong lithosphere that is hard for it to open up pore spaces for a melt to go through. So because melt cannot penetrate into this cold and strong lithosphere, it kind of creates this compaction pressure just below it that open up pore spaces just below it, so that melt can actually be piled up into what we call decompression layer, so that, and then it can flow towards the ridge axis. Okay, so to solve the equations that I showed, I developed a suite of models using terra firma, the transparent finite element rapid model assembler. The two-phase flow equations we are solving are discretized using finite element method and finite difference in time. We define our domain to be 100 kilometers deep and 200 kilometers wide, with the ridge axis right in the center. The top boundary is defined to be the moho, so anything on top is the crust. I don't really care too much about it because it's very brittle. And the top is spreading at a defined hot spreading rates. And the domain is kind of divided, as you can see here in blue, little triangles. That's the mesh. It is finer at the ridge axis to resolve the expected larger gradients. And the mesh coarsens away from the ridge, right at ridge axis so that it saves us computational time. So before I show you a video of the model results, I want to highlight what you'll be looking at. So on the left, you'll be looking at compaction pressure. Remember, this is the divergence of the solid velocity, so the compaction and expansion of the solid matrix, and that's modulated by the bulk viscosity. So you can think of the blue part here is kind of compressing so that it can allow pore spaces to form as the mantle starts to melt. And then on the right here, you have a porosity or melt fraction. So that's like in a percent, so 0.01 here would mean 1% volume fraction melt. And then in white, you have the melt flow line. So essentially, you can see the melt transport patterns. And again, this is 100 kilometers deep and 200 kilometers wide. Just a reminder that the time here is non-dimensional. So in this case, for 2 centimeters hot spreading rate, which is the model I'm going to show, the non-dimensional time is about 90,000 years. So for the full numerical time I'm going to show you, it's about 27 million years. Pretty amazing that you can see 27 million years in, you know, a few 10 seconds or so. So I'm showing the model with hot spreading rates of 2 centimeters per year, which is representative of slow spreading such as at Mid-Atlantic Ridge. So I'm gonna start here, hopefully it plays. So you can see right away it's kind of going through a transient state at the beginning, and you slowly kind of settle into this quasi-steady state. So 2 things I want to point out is, one, where the high melt regions are, and 2, how the general melt transport patterns. So right away you can see that there's quite a bit of melt right in the center, as shown here in the right column. And then also in this like wave-like train, and then at the decompaction layers right at the top. And there are 2 melt transport patterns here, one in the center where you get this melt flow lines in the center that's kind of being focused pretty deep towards the ridge axis where your melting rate is the highest. So melting rate is kind of highest in the ridge axis because that's where upwelling is the fastest. And away from this center region, melt is kind of generated and then buoyantly rising, and then it encounters this, it forms this porosity waves and it moves along in those wave packets and go towards the lithosphere where it piles up into this decompression layers and then moves towards the ridge axis. So that was 27 million years. Okay, so this is a snapshot of some of the models that I did to try to understand how permeability and spreading rate actually affects melt focusing. So on the left panel, you have the less permeable cases, and on the right, you have the more permeable cases. And going down the rows, you have increasing hot spreading rates. So you can kind of see here that one of the similarities between all these models are the location of the regions of high porosity. It's right in the heart of the models for all these models, and also at the decompaction layers. And you can also see there's kind of a 2 transport system mechanism that I was talking about. One that's kind of focusing melt in the center region, And then away from the ridge axis, you have melt kind of going to be rising. And the differences here really are between the more permeable and less permeable cases. In the less permeable cases, you have a lot more melt, about an order of magnitude more than the right-hand column where you have the more permeable cases. And you can think of it as when it's when the mantle matrix is less permeable, it means that the melt is retained more in the mantle matrix, and it kind of advects more with the mantle matrix. And when it's more permeable, it kind of leaves the mantle matrix where it was melting from, and it kind of moves out of it. So that's part of the reason why you see this less melt when it's more permeable. And another thing you see here is that the melt focusing in the center region is a lot more prominent for the more permeable case, whereas on the less permeable case, you kind of see this like just a little bit focusing in the center, and not too much horizontal melt transport in the center. So as I mentioned in the introduction, one of fundamental observation at mid-ocean ridges is the crustal thickness. We use two proxies in a model to predict the crustal thickness. One is the total melt produced in these models, and second is the total melt flux is coming out of the top boundary. So here is a plot of crustal thickness in kilometers over time in million years. So this is for the over the time domain for each model. And the colors are represents the spreading rates. So the top bit here is showing the crustal thickness that we can expect from the total melt produced in some of these models. And the bottom here is like the crustal thickness expected from the total melt flux. And you can see most of them kind of settle into a quasi-steady state, so it kind of gives a prediction of what the crustal thickness should be. And then you have this very wriggly pink line, and that's actually the model that was showing with the porosity waves. So you notice also there's a difference between the two of them, and that's because not all of the melt produced actually makes it out to form oceanic crust. Some of them actually freezes back into the lithosphere. So when I take an average of the models of the crustal thickness over time, this is kind of a plot that I get to try to understand what it looks like when we plot it against half spreading rates. So the triangles are from the total melt produced, and the circles are the expected crustal thickness from the melt flux. Again, you see the difference between them is essentially melt freezing into the lithosphere. And in black squares are from the compilation of seismic observation that I showed kind of in the introduction. And then the circles, gray circles, are from a more recent compilation of seismic data. So this is really just to show that our model prediction fits in pretty well with the observations. So now to go back to the question of pressure, how pressure gradients actually focuses melt, moves melt horizontally towards the ridge axis. I'm showing the different horizontal pressure gradients that's normalized by your buoyancy. Remember that any horizontal melt flow is going to have to be have the same order of magnitude as the buoyancy for it to matter, for it to actually move anything horizontally. So here on the left, I'm showing the dynamic pressure, and you can see it really only matters very, very close to the ridge axis. And on the right here, the middle and the right column are showing compaction pressure. The middle column is showing for the models with that is less permeable, and on the right is more permeable. And right away, you can see that the more permeable case has a much larger horizontal pressure gradients, which is the reason why we see this melt transport pattern to be so much more prominent than the less permeable models. So I hope I convinced you that this is a fairly clear-cut case. And that's actually a very simple reason for what's going on. So going back to Darcy's equation, melt segregates due to pressure gradients, and it's modulated by your permeability of the mantle. So when you look at the conservation of mass at quasi-steady state, which is essentially what all these models kind of evolve to, you have a balance in compaction pressure with the melting rate on the right, which is your gamma, and your bulk viscosity with zeta, and your density, solid density. So the solid density doesn't change in these models, and neither does the melting rate gamma. As you can see, the white contours here are the melting rates. So they don't really change very much between the less permeable case and the more permeable case. So what really matters is the bulk viscosity. And in this case, bulk viscosity is, the relation we use is shear viscosity over porosity. So before I was talking about how in a less permeable case, you tend to retain a whole bunch of melt. So your porosity is higher. And vice versa, for the more permeable case, you have more melt moving away from the region where it formed, and there's less melt retained. And so porosity is generally smaller. So here, because of this inverse relationship, for the less permeable case, you have higher melt, which means your bulk viscosity lower. And so your compaction pressure magnitude is lower as well. So it actually comes out of physics really nicely, which is not very often the case. So we were very excited about this, that we can explain this very elegantly. So now I'm back at this illustration where I show that on top of the two melt focusing mechanism that's been previously recognized, we also recognize this melting pressure mechanism that focuses melt very deep in the melting region. So you might start to wonder, okay, why do I care about this melting mechanisms at mid-ocean ridges? Why does it matter? Well, there are a lot of implications from it, and one of it is when we look at geophysical observations, we can look at this magnetotelluric inversion from Carey Key et al., and where they see this like really red blob that they interpret as melt. So this is a highly conductive region that they interpret as melt. And once you can kind of overlay the most fitting spreading rate model that we have, and you see that, okay, well, the deep focusing kind of coincides with the observed central melt region. That's pretty neat. But then you kind of see, well, I don't know, they don't really see this decompaction layers. Is it just missing because they see this very resistive region here where the melt is supposed to be? So where is the lithosphere, asthenosphere boundary, right? Is there something wrong with the models, or is the geophysical methods just unable to resolve them? Because you have to remember that the melt focusing mechanisms really matter, because this melting pressure focusing is the only mechanism that can focus melt before it even reaches the decompression layers. So if it is much stronger, that has implications for things like the asthenosphere, like viscosity. So one of the things I'm really excited about to work on right now is to understand, well, okay, let's go do forward modeling, geophysical forward modeling of both electromagnetic and seismic. So here I'm showing you some forward models that I'm collaborating with Samir Naif to do. So the top one here is the one with that's less permeable case, and the bottom one here is the one with larger permeability. And the Carla scale is actually the same as the one in Key et al. And you can see that there's a pretty big difference between them because of the amount of melt that's actually there. So this already tells us something that, okay, we probably want to have the larger permeability case because the patterns make more sense. But you notice that, well, it does not look red. So maybe we really do need a stronger melting pressure focusing where it's bringing much more melt to the center region. Then that's where you can get a red blob in the center. And of course, I'm also working with seismologists to understand whether they can actually resolve this when given the models that I have. So another thing that I'm have been working on is this really cool. I think in the videos you kind of see this porosity waves that are really neat. They start kind of in the melt generation zone and then they kind of propagate through up until they reach the cold strong lithosphere. So I've been working on what these porosity waves mean for ocean bathymetry with Ross and Jean-Arthur. So we were very fortunate. Well, okay, this is a strategy. We are using the data from the Malaysian airline 370 search off the coast of Australia. That's kind of situated close to the Southeast Indian Ridge. So we were able to look at this, get the data from the search and kind of split them into lines and look at the spectral data. So one of the things that's been highly debated fairly recently in the past 10 years is whether you can see any Milankovitch cycles in this bathymetric data. And so plotted in the dotted lines are the Milankovitch periodicity, so 100, 1,000 years, 41, and 23. So in this spectral data, what we kind of see is that, yeah, I'm not sure we can see any Milankovitch signal there, but what we do notice is that, well, there's also long period signals that's on the order of a few 100,000 years that is kind of not accounted for. So we thought, maybe this could be related to porosity waves. Let's run a model and see what happens. So I ran a model that has similar half spreading rates, and this is kind of in part A here is a plot of crustal thickness against numerical time. And so you can see there are quite a lot of wiggles in this plot, and that's mainly because of the porosity waves. And when you analyze this spectrally, you can see that, okay, we do see this long period signals in them. And this smaller periodicities are actually multiples of this longer periods. And so this is a possibility that maybe these porosity waves are, shows up in the bathymetry. And you have to remember, this is a very, very ideal case of 3.5 centimeters per year. Of course, I don't think the Earth works such that it's always going to be spreading at 3.5 centimeters per year. It's going to change over time, and that's probably why you get a wide spread of in the bathymetry. So hopefully, some conclusions. Hopefully, I've convinced you that melting pressure focusing is a very robust mechanism, and it really comes out of the equations. And that intrinsic permeability is very important for this melting pressure focusing, and also the rheological models, which I can talk about if anyone's interested. And the dominant focusing mechanism really matters for understanding the lithosphere, asthenosphere system. And lastly, that the porosity waves could really contribute to these long periods in ocean bathymetry. So I started off in the beginning, posing this big question of how continents form and how it co-evolve with these plate boundaries. So hopefully now that I have a better understanding of at least mid-ocean ridges in this talk that I've presented, I can slowly start to move towards early Earth, where we can play with parameters that are closer to early Earth, like a warmer, maybe more enriched mantle. And of course, I didn't really talk about any of my postdoc work that's like trying to understand this fluid flows at subduction zone and trying to understand carbon fluxes. And really, I do also want to take that and try to understand early Earth as well. So with that, I want to thank all my collaborators. I want to thank all of you for listening, and I'll take any questions.